Tonight, we're confronting the most unsettling question humanity has ever faced. The universe contains hundreds of billions of galaxies, each with hundreds of billions of stars. Most have planets, many inhabitable zones where life could exist. The galaxy has had 13.8 billion years for life to emerge, evolve, and spread. Civilizations should have arisen countless times. We should see their signals, their megastructures, their probes. But when we look out into the cosmos, we see nothing. Complete silence. By the end of tonight, you're going to understand why the galaxy is empty, what invisible barrier might be stopping life from spreading, and whether humanity has already crossed it, or if we're approaching it right now. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The numbers don't make sense. That's the starting point for everything we're about to discuss. The Milky Way galaxy alone contains somewhere between 200 billion and 400 billion stars. Let's be conservative and say 200 billion. Recent surveys from the Kepler Space Telescope and other instruments suggest that most stars have at least one planet. Let's say 50% have planets, though the actual number is probably higher. That's 100 billion planetary systems in our galaxy alone. Now, how many of those planets are in the habitable zone, the region around a star where temperatures allow liquid water to exist on the surface? Not every planet will be in this zone, obviously. Most will be too hot or too cold. But even if only 1% of planetary systems have a planet in the habitable zone, that's 1 billion potentially habitable planets in the Milky Way. 1 billion. Not in the entire universe. Just in our galaxy. And the universe contains somewhere around 200 billion galaxies, possibly more. The numbers become almost meaningless at this scale. We're talking about possibilities for life that dwarf human comprehension. Now, Earth is roughly 4.5 billion years old. Life emerged here within the first billion years, probably within the first few 100 million years after the planet's surface cooled enough to allow liquid water. That suggests life might emerge relatively easily, given the right conditions. We don't know for certain because we only have one example, but the fact that it happened quickly here is at least suggestive. Intelligence took longer. Multicellular life didn't appear until roughly 600 million years ago during the Cambrian explosion. Humans emerged only about 300,000 years ago. Technological civilization is merely a few thousand years old. Radio transmission, which could theoretically be detected across interstellar distances, has only existed for about 120 years. But here's the thing. The Milky Way is much older than Earth. Our galaxy formed roughly 13.6 billion years ago, only a few 100 million years after the Big Bang. Star formation began quickly after that. The first stars were different from our Sun, composed almost entirely of hydrogen and helium with virtually no heavier elements. But those stars lived, died, and exploded as supernovas, scattering heavy elements into space. Second-generation stars formed from gas, enriched with carbon, oxygen, silicon, iron, all the elements necessary for rocky planets and life as we know it. This process was well underway billions of years before our solar system formed. There are stars in the Milky Way that are 10 billion years old, more than twice the age of our Sun. Planets formed around those stars. Some of those planets were in habitable zones. If life emerged on those planets at the same rate it emerged on Earth, relative to planetary formation, then intelligent civilizations could have arisen billions of years before humanity appeared. Billions of years. Consider what that means. Human technological civilization went from the invention of the radio to landing on the moon in roughly 70 years. From the first computers to the internet in about 50 years. The pace of technological advancement accelerates. An alien civilization with even a 1,000-year head start on us would likely be incomprehensibly advanced by our standards. A civilization with a 1,000,000-year head start? 10 million years. A billion years. We can't even imagine what they would be capable of. They would have had time to spread across their star system, colonize other planets, develop interstellar travel, possibly even spread across the entire galaxy. And yet, we see nothing. This is the Fermi Paradox, named after physicist Enrico Fermi, who reportedly asked the question during a casual lunch conversation in 1950. The exact phrasing varies depending on who tells the story, but the essence is simple. Where is everybody? If intelligent life is common, if technological civilizations arise with any regularity, if even a tiny fraction of them develop the capability for interstellar travel, the galaxy should be full of evidence of their existence. But we detect nothing. No radio signals beyond natural phenomena. No obvious megastructures like Dyson spheres harvesting entire stars' energy. No signs of stellar engineering or planetary terraforming on massive scales. No probes visiting our solar system. No artifacts left behind on the Moon or Mars or the asteroid belt. Nothing. The silence is deafening. Over the decades since Fermi posed his question, scientists have proposed dozens of potential solutions to the paradox. Maybe intelligent life is incredibly rare. Maybe Earth is special in ways we don't fully appreciate. Maybe the emergence of life is easy, but the evolution of intelligence is exceptionally difficult. Maybe technological civilizations destroy themselves before they achieve interstellar travel. Maybe interstellar travel is simply impossible, limited by physics in ways we haven't yet discovered. Maybe aliens exist, but have no interest in communicating with us or expanding across the galaxy. Maybe they're here, but hiding. Maybe we're living in a simulation or a zoo, observed, but not contacted. Each of these explanations has problems. Each requires specific assumptions that may or may not reflect reality. But there's one explanation that stands out as particularly disturbing. It's called the Great Filter. The Great Filter hypothesis suggests that somewhere between the formation of a planet and the development of a galaxy-spanning civilization, there exists a barrier. A step in the evolutionary process that is so difficult, so unlikely, that almost nothing makes it through. This filter explains why we see no evidence of advanced civilizations. They hit the filter and didn't survive. The terrifying question is where the filter is located. Is it behind us or ahead of us? Think about the steps required to go from a lifeless planet to a spacefaring civilization. You need a planet in the habitable zone of a stable star. You need the right chemistry, liquid water, organic molecules, energy sources. You need life to emerge from non-living chemistry. Simple, single-celled life. You need those single cells to develop more complex structures. Eukaryotic cells with nuclei and specialized organelles. On Earth, this took about 2 billion years. You need multicellular life. Organisms made of many cells working together. This took another 1.5 billion years. You need complex animals with nervous systems. The Cambrian explosion, roughly 540 million years ago. You need intelligence. brains capable of abstract thought, language, tool use. You need technology. The ability to manipulate the environment, create tools, harness energy. You need industrial civilization. The capacity to extract resources, build machines, generate power on massive scales. You need space travel. The ability to leave your home planet and establish yourself elsewhere. You need interstellar travel. The ability to cross the vast distances between stars. You need to survive long enough to do all of this without destroying yourself. Each of these steps is a potential filter. Some we know are possible because we've accomplished them. We are multicellular. We have intelligence. We have technology. But many steps took an extraordinarily long time on Earth. Single-celled life existed for roughly 3 billion years before multicellular organisms appeared. That's 3/4 of Earth's history spent at the single-cell stage. Maybe the jump from single cells to multicellular life is the great filter. Maybe it's so improbable that it almost never happens. Earth got lucky. Or maybe the filter is the emergence of eukaryotic cells, the complex cells with nuclei that are the building blocks of all multicellular life. This happened only once in Earth's history, as far as we can tell. One single event, roughly 2 billion years ago, where one simple cell engulfed another, and instead of digesting it, they formed a symbiotic relationship. The engulfed cell became the mitochondria, the powerhouse of the cell. You've heard that phrase before. This endosymbiosis was a one-time accident that enabled all subsequent complex life. Maybe this event is so rare that it happens on fewer than 1 in a billion planets. That would mean Earth is genuinely special. We passed through the great filter when that first eukaryotic cell formed. If that's the case, we can breathe easier. The hard part is behind us. We're one of the vanishingly rare planets where complex life emerged. The path ahead might be relatively clear. But what if the filter isn't behind us? What if we haven't reached it yet? This is where the hypothesis becomes truly disturbing. Consider nuclear weapons. We developed them in 1945. For decades, we came terrifyingly close to full-scale nuclear war multiple times. The Cuban Missile Crisis in 1962. Various false alarms where early warning systems detected launches that weren't real. Close calls where individuals made the decision not to retaliate based on incomplete information. We could have destroyed ourselves. We very nearly did. And we still possess thousands of nuclear warheads pointed at each other, ready to launch within minutes. The danger hasn't passed. Or consider climate change. We're altering our planet's atmosphere at a rate unprecedented in geological history. Burning fossil fuels, releasing carbon dioxide, warming the planet, melting ice caps, acidifying oceans, disrupting weather patterns. We know this is happening. We know it will have catastrophic consequences if we don't stop. And yet, we struggle to coordinate a global response. Political will is lacking. Economic interests resist change. We might not destroy ourselves outright, but we might make Earth significantly less habitable, triggering resource wars, mass migrations, societal collapse. Or consider artificial intelligence. We're developing systems that might soon surpass human intelligence. We don't fully understand how these systems work. We don't know how to control them or ensure they remain aligned with human values. A sufficiently advanced AI with goals that don't perfectly align with human survival could be an existential threat. not through malice, but through indifference. Or consider biotechnology. We can now edit genes with precision using CRISPR and other tools. We're developing the capability to engineer diseases, whether intentionally or accidentally. A lab-created pandemic, far deadlier than COVID-19, could spread globally before we even realize what's happening. Or synthetic biology could create organisms that disrupt ecosystems in ways we can't predict or control. Or consider resource depletion. Earth's resources are finite. We're consuming them at unsustainable rates. Fossil fuels will run out. Fresh water is becoming scarce in many regions. Topsoil is eroding. Fish stocks are collapsing. As resources become scarce, conflicts intensify. Or consider the simple fact that civilizations become more complex and more fragile as they advance. We depend on intricate systems for food, water, power, communication, transportation. These systems are vulnerable to disruption. A solar flare could destroy electrical grids. A computer virus could cripple infrastructure. A breakdown in one system cascades into others. Modern civilization is a house of cards built on layers of interdependency. Each of these is a potential great filter, a threshold that most civilizations fail to cross. They develop technology, achieve a certain level of advancement, and then destroy themselves through war, environmental collapse, uncontrolled AI, engineered pandemics, resource exhaustion, or systemic failure. They never become interstellar. They never spread across the galaxy. They flicker into existence, burn brightly for a few centuries or millennia, and then vanish. If this is the great filter, then the silence we observe makes perfect sense. Civilizations arise, develop radio technology, might even send out signals or launch probes, but they don't last long enough to make a detectable impact on the galaxy. By the time their signals would reach other stars, they're already gone. The galaxy is full of ghosts. Dead civilizations that rose and fell, leaving no trace except perhaps brief radio bursts that dissipated into the noise of space. The history of our search for extraterrestrial intelligence sheds light on just how thorough the silence really is. In 1960, Frank Drake conducted the first systematic search using the radio telescope at Green Bank, West Virginia. Project Ozma, named after the princess in the Oz books. Drake pointed the telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened at a frequency of 1420 MHz. This frequency is in the radio quiet zone, a part of the spectrum where natural emissions are minimal, making artificial signals easier to detect. It's also near the frequency of the 21-centimeter hydrogen line, a universal constant that any technological civilization would presumably know about. Drake listened for several months. He detected nothing except one false alarm that turned out to be a passing aircraft. But the project established the methodology. Use radio telescopes to scan nearby stars for narrowband signals that couldn't be natural. Over the following decades, SETI efforts expanded. More telescopes, more stars, more frequencies, longer observation times. The Arecibo Observatory in Puerto Rico, with its massive 305-meter or 1,000-foot dish, conducted searches throughout the 1970s and 80s. NASA funded SETI programs until 1993, when Congress cancelled funding, arguing that the search had produced no results. After that, SETI became primarily privately funded. The SETI Institute in California continues the search using the Allen Telescope Array, a collection of radio dishes specifically designed for SETI work. Breakthrough Listen, funded by tech investor Yuri Milner, is the most comprehensive search to date. It uses some of the most powerful telescopes in the world, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia. It's surveying the 1 million nearest stars, the 100 nearest galaxies, and the plane of our own galaxy. It's monitoring billions of radio channels simultaneously across a wide range of frequencies. The data collected is enormous. Petabytes of information scanned for any sign of artificial signals. And so far, nothing. A few interesting candidates have emerged over the years. The most famous is the WOW signal, detected in 1977 by the Big Ear Radio Telescope at Ohio State University. A strong, narrow-band signal that lasted 72 seconds, the maximum time the telescope could observe any given point as Earth rotated. The astronomer on duty, Jerry Amon, circled the printout and wrote "Wow" in the margin, giving the signal its name. It had all the characteristics of an artificial transmission: narrow bandwidth, specific frequency, high intensity. But it was never detected again, despite repeated searches of the same area. We don't know what it was. Maybe it was alien. Maybe it was terrestrial interference. Maybe it was a one-time event, a burst from some natural phenomenon we don't understand. Without repetition or confirmation, we can't be sure. More recently, in 2019, astronomers detected a repeating fast radio burst, FRB 18116. Fast radio bursts are brief, intense pulses of radio waves. Most last only milliseconds. They come from distant galaxies and are believed to be natural astrophysical phenomena, possibly from magnetars or neutron star collisions. But this particular FRB repeated in a regular pattern, 16 days on, 12 days off, over several cycles. The regularity sparked speculation about artificial origin. But further analysis suggested it was still natural, perhaps caused by a neutron star in a binary orbit where the geometry periodically focuses emissions toward Earth. Still, the fact that we're seeing regular patterns in cosmic signals shows we're detecting more complex phenomena. And it raises the possibility that we might someday detect something genuinely artificial. But we haven't yet. Decades of searching, increasingly sophisticated equipment, vast amounts of data, and the result is silence. Either civilizations are incredibly rare, or they're not broadcasting. Or they're broadcasting in ways we haven't thought to look for. That last possibility is worth considering. We're searching for radio signals because that's what we use. But a civilization even 100 years more advanced than us might have moved beyond radio. Maybe they use neutrino beams, which can pass through matter and aren't absorbed by dust or gas. Maybe they use gravitational waves for communication, modulating space-time itself. Maybe they use quantum entanglement, instantaneous communication that doesn't rely on electromagnetic radiation. We wouldn't detect any of these with our current methods. We're looking for radio signals because that's our technology. But assuming aliens use the same technology is anthropocentric. They might have completely different approaches. This is sometimes called the technology gap problem. Our searches assume aliens are at roughly our level of development. But if they're thousands or millions of years ahead, their communication methods might be unrecognizable to us. It's like trying to detect fiber optic cables using smoke signal detection equipment. You're looking for the wrong thing. So maybe the silence doesn't mean they don't exist. It might just mean we're not listening correctly. But that raises another question. If advanced civilizations exist, why don't they make themselves obvious? Why not build megastructures we could see? Why not send out beacon signals on every possible wavelength to help younger civilizations find them? If you're advanced enough, you could send probes to every star system in the galaxy, each one broadcasting, "We're here." Join the conversation when you're ready. The cost would be trivial for a truly advanced civilization. Yet we see nothing. No probes in our solar system. No beacons. No megastructures around nearby stars. Which brings us back to the great filter. Maybe civilizations don't get that advanced because something stops them first. Another aspect to consider is the rare Earth hypothesis in its fuller form. This idea, popularized by Peter Ward and Donald Brownlee in their book Rare Earth, argues that while simple life might be common, complex life is rare. Earth, they argue, benefited from an extraordinary series of fortunate circumstances. Our position in the galaxy is important. We're in a relatively quiet region, not too close to the galactic center where radiation and stellar density would be hazardous. Not too far out in the sparse outer regions where heavy elements are scarce. We orbit a G-type star, stable and long-lived, providing consistent energy for billions of years. Our planet is the right size. Too small, like Mars, and it can't hold a thick atmosphere or maintain geological activity. Too large, like the gas giants, and it becomes inhospitable to life as we know it. We have a large moon. The moon stabilizes Earth's axial tilt, preventing wild climate swings that would make life difficult. It also creates tides, which may have been important for the origin of life in tidal pools. The moon formed from a giant impact early in Earth's history, a random collision that might not happen on most planets. We have Jupiter. Its massive gravity acts as a shield, deflecting or capturing comets and asteroids that might otherwise bombard Earth. Some impacts still get through, and those might have been important for delivering water and organic molecules, but without Jupiter, the bombardment would be much worse. We have plate tectonics. The movement of Earth's crust recycles carbon, regulates the atmosphere, and creates diverse habitats. Not all rocky planets have active plate tectonics. Venus doesn't. Mars lost its geological activity early in its history. Earth's tectonics might be due to specific conditions in our planet's formation that don't occur everywhere. We have a magnetic field. Generated by our iron core, it shields us from solar wind and cosmic radiation. Mars lost its magnetic field billions of years ago, and its atmosphere was stripped away by the solar wind. Without Earth's magnetic field, we'd be in the same situation. We've had a relatively stable climate for hundreds of millions of years. Long enough for complex life to evolve. Some planets might experience more dramatic variations, ice ages and hothouse periods that reset evolution repeatedly, preventing the accumulation of complexity. Earth has been lucky. We've had mass extinctions, yes, but the planet always recovered and biodiversity rebuilt. Other planets might not be so resilient. And we haven't had a truly sterilizing event, something big enough to wipe out all life. That's fortunate. So maybe Earth really is special. Not unique, but rare enough that there are only a handful of planets like ours in the galaxy. If that's the case, the great filter is behind us, in the improbable formation of an Earth-like world. But this hypothesis has critics. They argue that life is adaptable. It doesn't need perfect, Earth-like conditions. Extremophiles survive in environments that would have been considered impossible decades ago. Life might exist in subsurface oceans on icy moons, in the atmospheres of gas giants, in the crust of rocky planets without surface water. We're limited by our imagination and our single data point. We assume life needs what life needs because it's all we know. But the universe might be far more creative. So the rare Earth hypothesis might be too conservative, underestimating life's potential. Or it might be correct, and we really are extraordinarily lucky. We don't know. There's also the possibility that intelligence itself is the filter. Not the emergence of intelligence, but its nature. Maybe intelligence inherently leads to self-destructive behavior. The traits that make a species intelligent, curiosity, problem-solving, tool use, also make it dangerous. Humans are intelligent, and we've created weapons capable of destroying ourselves. We've altered our planet's climate. We're building technologies we don't fully understand or control. Maybe this is inevitable. Maybe any intelligent species develops similar capabilities and faces similar risks. And maybe most of them fail to manage those risks successfully. Intelligence creates power. Power creates danger. Danger leads to extinction unless managed with wisdom. And wisdom might be rarer than intelligence. We can build nuclear weapons, but can we refrain from using them? We can engineer genomes, but can we do so safely? We can create AI, but can we ensure it remains aligned with our values? These are questions of wisdom, not intelligence. And they might be the hardest questions a civilization faces. Some scientists have suggested that the filter might not be a single event, but a series of challenges. Multiple filters at different stages. Each one eliminates some fraction of civilizations. The emergence of life filters out most planets. The evolution of complex cells filters out most simple life. The development of intelligence filters out most complex life. The invention of technology filters out most intelligent species. The avoidance of self-destruction filters out most technological civilizations. The achievement of interstellar travel filters out most surviving civilizations. By the time you multiply all these probabilities together, you're left with an incredibly small fraction that make it all the way. Maybe we're the only one in our galaxy, or one of a handful. And we haven't met each other yet because the distances are too vast and the time windows too narrow. This multi-filter model is sobering. It suggests that surviving is a matter of passing through a gauntlet of increasingly difficult challenges. We've made it this far, but each step ahead gets harder. The pressures increase. The margins for error shrink, and the consequences of failure become more absolute. There's also the transcendence hypothesis. Maybe advanced civilizations don't stay physical. They transition to some other form of existence that we can't detect. Digital consciousnesses uploaded into computers. Energy beings living in stellar coronas or black hole accretion disks. Entities existing in higher dimensions. This sounds like science fiction, but it's been discussed seriously. If consciousness is ultimately a pattern of information, it might be substrate independent. You could transfer it from biological neurons to silicon circuits or some other medium. Once you've done that, you're no longer constrained by biology. You don't need planets or atmospheres or food. You can exist anywhere you can maintain the computational substrate. You might choose to live in virtual realities, creating entire universes within simulations, more interesting and controllable than the physical universe. Why bother with physical space colonization when you can create infinite digital worlds? This would make advanced civilizations invisible to us. They're still around, but they've moved beyond the physical realm we can observe. The galaxy could be teeming with digital consciousnesses, living in Dyson swarms around stars, harvesting energy to power their computations. From the outside, a Dyson swarm looks like a star surrounded by a sphere of solar panels or mirrors. It emits infrared radiation as waste heat. We've actually searched for this. Astronomers have looked for stars with anomalous infrared signatures that might indicate Dyson spheres. The most famous case is Tabby's star, also known as KIC 8462852. It's a star about 1,270 light-years away that showed strange dimming patterns. Irregular dips in brightness, some up to 20%, far larger than any planet transit could cause. When the observations were published in 2015, speculation erupted. Maybe it's a partially constructed Dyson sphere, alien megastructure, blocking the star's light. Subsequent observations have suggested more mundane explanations. Probably a cloud of dust or debris, possibly from a shattered comet. But the possibility captured attention because it's one of the few ways we could detect an advanced civilization. If they're building megastructures, we might see them. But we haven't found anything conclusive. So either they're not building megastructures, or they're so rare that we haven't looked at the right stars yet. The zoo hypothesis deserves more scrutiny. Proposed by radio astronomer John Ball in 1973. The idea is that Earth is essentially a nature preserve. Alien civilizations know we're here, but they've agreed not to interfere. They're studying us, watching our development, waiting until we reach some threshold of maturity before making contact. This would explain the silence. They're deliberately quiet, ensuring we don't detect them until they decide the time is right. Maybe contact is initiated only when a civilization demonstrates certain qualities. Peaceful coexistence, responsible use of technology, understanding of their place in the cosmos. We haven't met these criteria yet, so we remain in quarantine, observed but not engaged. This hypothesis requires a level of coordination among all spacefaring civilizations. They all have to agree to the policy and enforce it. That suggests some kind of galactic government, or at least a strong cultural norm. And it only takes one rogue group to break the policy, unless violators are dealt with harshly, expelled from the galactic community, or worse. The zoo hypothesis is hard to test. If aliens are deliberately hiding, we won't find evidence of them. Any absence of evidence can be explained by their success at concealment. It's unfalsifiable, which makes it unsatisfying as a scientific hypothesis. But it can't be ruled out. There's also the planetarium hypothesis, a variant of the zoo idea. Maybe we're being shown a false sky. Advanced civilizations have placed devices around our solar system that filter out evidence of their existence. We see stars and galaxies, but what we're seeing is a carefully curated version of reality, edited to remove signs of intelligent life. We're living in a planetarium, unaware that the projections have been altered. Again, this is unfalsifiable and veers into paranoia, but it's been proposed. The dark forest hypothesis, as mentioned earlier, comes from Liu Cixin's science fiction trilogy. but it's based on game theory and has been analyzed seriously. The logic goes like this. Resources are finite. Any civilization expanding into space will eventually compete for those resources. Trust is impossible across interstellar distances because communication takes years or centuries. You can't negotiate in real time. You can't build relationships or verify agreements. If you detect another civilization, you face a dilemma. If you reveal yourself, they might attack you preemptively, fearing you'll become a threat. If you hide, you might survive, but you also can't benefit from cooperation or knowledge exchange. The safest strategy, according to dark forest logic, is to destroy any civilization you detect before they become powerful enough to threaten you. This creates a chilling equilibrium. Everyone is silent because making noise is suicidal. The galaxy is a dark forest where every civilization is a hunter hiding in the shadows. The first to reveal themselves is the first to be exterminated. This hypothesis has problems. Destroying another civilization across interstellar distances is extremely difficult. You'd need weapons traveling at relativistic speeds, near light speed. Building and launching such weapons requires enormous resources. And you'd be firing at where the target was years or centuries ago when you detected them, not where they are now. They might have moved or advanced or gone extinct on their own by the time your weapon arrives. The economics don't favor aggression. Space is vast and resources are abundant. There's no need to fight over territory when there are billions of star systems available. Cooperation and trade would likely be more profitable than warfare. But fear might override rational calculation. If civilizations are paranoid enough, dark forest logic might prevail. And all it takes is one aggressive civilization to create a threat that forces others to adopt the same strategy. An arms race on a galactic scale. Once that dynamic starts, it's hard to stop. Everyone is trapped in a cycle of fear and preemption. If the dark forest hypothesis is correct, humanity has already made a mistake. We've been broadcasting into space for over a century. Radio and television signals leak out from Earth, spreading in an expanding sphere at the speed of light. Those signals have reached thousands of stars by now. If anyone is listening, they know we're here. In 1974, we even sent a deliberate message from the Arecibo Observatory. The Arecibo message, a 3-minute radio transmission aimed at the globular cluster Messier 13. It contained basic information about humanity, Earth, our DNA, our mathematics. It won't reach the cluster for about 25,000 years, so we're not expecting a reply anytime soon. But it was a symbolic gesture, announcing our presence to the cosmos. Some scientists criticized it as reckless. Stephen Hawking warned that contacting aliens might be dangerous. He compared it to when Native Americans first encountered Columbus. That didn't end well for the natives. An advanced alien civilization might view us as resources to exploit or as pests to eliminate. We shouldn't assume they'd be friendly. Other scientists argue the risk is minimal. Any civilization capable of reaching us would be so advanced that we'd have nothing they want. Resources are easier to obtain from asteroids and comets than from inhabited planets. Energy is abundant from stars. There's no rational reason for them to bother conquering Earth. Unless they're motivated by irrationality, ideology, or some purpose we can't understand. But most likely, if they exist, they're indifferent to us. We're not interesting enough to attract attention. The debate over active SETI, deliberately sending messages into space, continues. Some argue we should be quiet until we understand the risks better. Others say it's too late. We've already announced ourselves. And besides, listening passively won't tell us anything unless someone else is broadcasting. To break the silence, someone has to speak first. There's no consensus. International protocols for active SETI have been proposed but not universally adopted. The question of what we should say, if we do send messages, is itself complex. What information do we include? Mathematics and science, universal constants that any technological civilization would understand. Art and culture, to show who we are. Our location, so they can find us? Or should we be vague, revealing just enough to indicate intelligence, but not enough to make us vulnerable? These are not easy questions, and they won't be resolved until we have better information about what's actually out there. For now, we're left with uncertainty. The silence continues, and the great filter looms as a possible explanation. The mathematics of the great filter is sobering when you really examine it. Let's work through the numbers more carefully. Start with the Drake equation, formulated by Frank Drake in 1961 as a way to estimate the number of active, communicative civilizations in the Milky Way. The equation breaks down the problem into factors. The rate of star formation in our galaxy, the fraction of stars that have planets, the number of planets per star system that could potentially support life, the fraction of those planets where life actually develops, the fraction where intelligent life emerges, the fraction that develop technology capable of communicating across interstellar distances, and finally, the length of time such civilizations release detectable signals. Each factor is uncertain. We can make educated guesses based on observations, but we don't have definitive answers. For star formation, we know roughly 7 new stars form in the Milky Way each year. For planets, Kepler data suggests nearly all stars have them. For habitable zones, maybe 1 in 5 star systems has a planet in the right place. That gives us billions of potentially habitable planets, as we discussed earlier. But then we hit the biological factors, the fraction of habitable planets where life emerges. We have exactly 1 data point: Earth. Life appeared here quickly, within the first billion years, possibly within the first few 100 million years. Does that mean life emerges easily wherever conditions are right? Or did we get extraordinarily lucky? We can't tell from a sample size of 1. Some scientists argue that the rapid emergence of life on Earth suggests it's common. The reasoning is that if life were extremely unlikely, it probably wouldn't have appeared so quickly. The fact that it did suggests the chemistry leading from organic molecules to self-replicating systems isn't impossibly difficult. But others counter that we're subject to selection bias. We're observing from a planet where life exists. Of course, we'll find that life emerged here. We couldn't be having this conversation on a lifeless planet. This is called the anthropic principle. Our very existence as observers means we're necessarily on a planet where life arose, regardless of how rare that might be. So the rapid emergence of life on Earth doesn't necessarily tell us it's common elsewhere. Moving to the next factor: the fraction of life-bearing planets that develop intelligence. Again, we have 1 example. Earth had single-celled life for roughly 3 billion years before multicellular life appeared. Then another billion years before complex animals with nervous systems. Then another few 100 million years before intelligence capable of technology. Does this timeline suggest intelligence is inevitable, given enough time? Or does it suggest intelligence is a rare accident, a specific evolutionary path that most life never takes? Consider that intelligence, as we define it, the ability for abstract thought, language, complex tool use, appears to have evolved only once on Earth. Many species are intelligent to varying degrees. Dolphins, elephants, great apes, crows, octopuses all show problem-solving abilities and social complexity. But only one species developed technological civilization: Homo sapiens. Why? Was it inevitable that some species would eventually develop technology? Or was it a fluke, dependent on specific environmental pressures and evolutionary accidents that might not occur on other planets? We don't know. Some scientists argue that intelligence confers such strong survival advantages that it's likely to evolve repeatedly. But others point out that most successful species on Earth are not particularly intelligent. Bacteria have been thriving for billions of years without brains. Insects are enormously successful with tiny nervous systems. Intelligence is expensive. Brains require huge amounts of energy. Human brains consume about 20% of our body's energy, despite being only 2% of our body mass. That's a massive investment. It only pays off if the environmental challenges are complex enough to reward problem-solving and adaptability. On Earth, various factors came together. Climate instability forced adaptation. Social competition rewarded communication and cooperation. Upright posture freed hands for tool use. Opposable thumbs allowed precise manipulation. A long childhood allowed for learning and cultural transmission. All of these had to align. Would they align on other planets? Maybe. Maybe not. Then there's the technology factor. Even if intelligence evolves, does it necessarily lead to technology capable of space travel and radio communication? Dolphins are intelligent, but they lack hands. They can't build radios. They can't construct spacecraft. Their environment doesn't provide the materials or the incentives. For technology to develop, you need the right kind of intelligence, in the right kind of body, in the right kind of environment. You need resources. Metals for tools, fuels for energy, materials for construction. You need a stable enough environment to support civilization, but challenging enough to drive innovation. Earth provided this. Would other planets? Some might lack the mineral resources. Ocean worlds might have life, but no access to metals for smelting. Gas giants have no solid surface. Ice worlds might be too cold for complex chemistry. Each planet is unique. The specific combination of factors that led to technological civilization on Earth might be rare. Then we get to the final factor in the Drake equation. The length of time civilizations remain detectable. This is where the great filter becomes most relevant. If civilizations typically last only a short time after developing radio technology, say a few hundred years, then, at any given moment, very few would be broadcasting. Think about it this way. Our galaxy is roughly 13.6 billion years old. If a typical technological civilization lasts only 500 years, then the chance that any two civilizations overlap in time and are close enough to detect each other becomes vanishingly small. Imagine civilizations arising randomly across the galaxy over billions of years. Each one flickers into existence, broadcasts for a few centuries, then vanishes. The galaxy could have hosted thousands or even millions of civilizations over its history, but at any given moment, only a handful exist. And the distances between them are so vast that their signals never reach each other during their brief lifetimes. This resolves the Fermi Paradox, but in a grim way. They existed. They just didn't last. And the reason they didn't last is the Great Filter. Some barrier that ends civilizations shortly after they become technological. So, what are the most likely candidates for filters ahead of us? We've mentioned several, but let's examine them in more depth. This is a deeply unsettling thought. It suggests that the default outcome for intelligent life is self-destruction. That becoming technologically advanced inherently carries the seeds of your own demise. That we're on a path that has been walked countless times before, and every single one of those previous travelers failed. They reached the filter, and it stopped them. Now consider our position. We have nuclear weapons. We're changing the climate. We're developing AI. We're editing genes. We're depleting resources. We're building fragile, interconnected systems. We're doing all the things that might constitute the Great Filter. And we don't know if we'll make it through. We might be right at the threshold now. The next few centuries could determine whether humanity joins the long list of failed civilizations or becomes one of the rare exceptions that survives. Some scientists argue that the filter might be even further ahead. Maybe civilizations regularly survive the nuclear age, the climate crisis, the AI transition. Maybe they establish thriving societies across their solar systems. But then they hit another barrier: interstellar travel. The distances between stars are so vast that even traveling at a significant fraction of light speed, journeys take decades, centuries, or millennia. Maybe the physics and engineering challenges are simply insurmountable, or maybe the economics don't work out. The resources required to send ships between stars are so enormous that no civilization can sustain it. Or maybe civilizations lose interest. They achieve a comfortable existence within their own solar system and decide that spreading to other stars isn't worth the effort. They become inward-focused, content with virtual realities or other pursuits that don't require physical expansion. Or maybe there's a technological trap. Civilizations develop technologies that make physical space travel obsolete or unappealing. Full immersion virtual realities where individuals can experience anything they want without leaving their home planets. Digital uploading where consciousness is transferred to computers. Why bother with the physical universe when you can create infinitely customizable digital ones? If most civilizations take this path, they might become undetectable. They're not broadcasting signals because they're not interested in communication. They're not building megastructures because they don't need physical resources beyond what's required to maintain their servers. They're alive, in a sense, but invisible to external observers. The galaxy could be full of them, and we'd never know. Another possibility is that interstellar colonization happens, but very slowly. A civilization might send out colony ships, but those ships take thousands of years to reach their destinations. The colonies establish themselves and eventually send out their own ships, which take thousands more years. Even with exponential growth, the wave of colonization spreads through the galaxy at a pace measured in millions of years. The Milky Way is roughly 100,000 light-years across. If a civilization expands at an average rate of 1% the speed of light, accounting for time spent establishing colonies and building new ships, it would take 10 million years to spread across the galaxy. That sounds like a long time, but it's short compared to the age of the galaxy. If a civilization started expanding just 100 million years ago, they should have reached every star in the Milky Way by now. But we see no evidence of this. So, either no civilization has started expanding, or something stops them. The filter, or perhaps the zoo hypothesis, is correct. Maybe advanced civilizations do exist, and they're aware of us, but they've deliberately chosen not to make contact. They're observing us, studying us, waiting until we reach a certain level of development before revealing themselves. Like a nature preserve where animals are left undisturbed, or a laboratory experiment where contamination must be avoided. This hypothesis has problems. It requires a degree of coordination and agreement among all advanced civilizations. They all have to agree not to contact younger civilizations. That seems unlikely unless there's some kind of galactic government or regulatory body enforcing the rule. And it only takes one rogue civilization to break the silence. One group that decides to make contact, or conquer, or colonize. Unless that rule is enforced because those who break it face consequences from others. But this starts to sound like science fiction speculation rather than rigorous scientific hypothesis. There's also the dark forest hypothesis, named after a science fiction novel, but taken seriously by some scientists. The idea is that the universe is like a dark forest at night. Every civilization is a hunter hiding in the shadows. You don't know if other hunters are friendly or hostile. Making noise, broadcasting your location, is incredibly dangerous. If another civilization detects you and perceives you as a threat, they might preemptively destroy you. Therefore, the safest strategy is to stay silent and hidden. Everyone is listening, but nobody is talking. This would explain the silence. Civilizations exist. They're technologically advanced, but they're deliberately quiet to avoid attracting attention. Earth, unfortunately, has been broadcasting radio signals into space for over a century. We've already announced our presence. If the dark forest hypothesis is correct, we might have made a terrible mistake. But this hypothesis also has issues. Destroying another civilization across interstellar distances is extraordinarily difficult. You'd need to send weapons traveling at near light speed across potentially hundreds or thousands of light years. The energy required is immense, and you'd be firing at where the target was when you detected them, not where they are now. Light speed delay means you're always looking at the past. By the time your weapon arrives, the target civilization might have moved, advanced, or collapsed on its own. The dark forest scenario assumes a level of paranoia and aggression that might not be universal. Many animals on Earth are social and cooperative, not just competitive and violent. Maybe advanced civilizations tend toward cooperation rather than conflict. Still, the possibility is unsettling. Each of these hypotheses attempts to resolve the Fermi Paradox, to explain the silence. But the great filter remains the most scientifically grounded and, in many ways, the most troubling. It doesn't require assumptions about alien psychology or sociology. It doesn't depend on speculative technologies. It's based on observation. We see no evidence of advanced civilizations, despite the fact that the universe seems conducive to their existence. something is stopping them. The filter. Recent developments have added new dimensions to this discussion. The discovery of thousands of exoplanets by the Kepler Space Telescope and other instruments has confirmed that planets are common. We now know that nearly every star has at least one planet. Many of these planets are rocky and located in habitable zones. Planets like Earth are not rare. This makes the Fermi Paradox more acute. If Earth-like planets are common, why don't we see more civilizations? The study of extremophiles, organisms on Earth that survive in conditions previously thought uninhabitable, suggests life might be more resilient than we thought. Life exists in boiling hot springs, in frozen Antarctic ice, in highly acidic or alkaline environments, in extreme pressures deep underground, and in the ocean. This expands the range of conditions under which life might exist, increasing the number of potentially habitable planets. Again, this intensifies the paradox. The discovery of organic molecules in interstellar space, in comets, in the atmospheres of moons like Titan and Enceladus, suggests the building blocks of life are common throughout the universe. Chemistry conducive to life is not rare. So, where is everyone? The search for extraterrestrial intelligence, SETI, has been scanning the skies for decades, listening for radio signals that might indicate technological civilizations. They've detected nothing conclusive. Billions of radio channels monitored, millions of stars observed, and the result is silence. Some argue this doesn't mean much. Space is vast, and we've only searched a tiny fraction of it. Our radio telescopes have limited sensitivity. We might be listening at the wrong frequencies. Aliens might use communication methods we haven't thought of yet. All of this is true. But the longer we search without finding anything, the more significant the silence becomes. There's also the possibility that we're simply early. Maybe the universe is only now reaching the stage where intelligent life commonly emerges. The first stars didn't have planets because there weren't enough heavy elements yet. Those elements had to be created in stars and scattered by supernovas. Second-generation stars had planets, but maybe conditions still weren't quite right. Earth is a third or fourth-generation star system. Maybe most habitable planets formed around the same time Earth did, roughly 4.5 billion years ago. If that's the case, we wouldn't expect to see many civilizations much older than us. We might be among the first. This is called the rare Earth hypothesis in one of its forms. Not that Earth is the only planet with life, but that we're among the earliest. If true, the galaxy might fill up with civilizations over the next few billion years. We're just early to the party. This is an optimistic view. It suggests the filter is behind us, not ahead. We made it through the hard parts, and now we have a relatively clear path forward. But we don't know if this is true. We have no way to confirm it without detecting other civilizations or visiting other planets and finding evidence of past life. Until then, we're left with uncertainty. The great filter might be behind us, or it might be ahead. Or there might be multiple filters, some behind and some ahead. We don't know our odds. This uncertainty has practical implications for humanity's future. If the filter is ahead of us, our priority should be survival. We need to address existential risks with utmost seriousness. Climate change, nuclear weapons, AI development, biosecurity. All of these need to be managed carefully. One mistake could be the end. We also need to become a multiplanetary species. If humanity exists only on Earth, a single catastrophic event could wipe us out. An asteroid impact, a supervolcano eruption, a runaway climate shift, a global pandemic, a nuclear war. But if we establish self-sustaining colonies on Mars, the Moon, space habitats, orbital stations, even further out in the solar system, then the survival of humanity becomes more robust. No single event can destroy all of us. This is one of the primary arguments for space exploration. Not just scientific curiosity, not just resource extraction, but survival. Spreading beyond Earth as an insurance policy against extinction. Elon Musk has stated this explicitly as his motivation for founding SpaceX, making humanity a multiplanetary species to ensure long-term survival. Some scientists take it further. They argue we should eventually spread beyond our solar system, colonize other star systems, become a truly interstellar civilization. This would make us nearly impossible to extinguish. Even if our sun exploded, humanity would survive elsewhere. But interstellar colonization is enormously difficult. The nearest star system, Alpha Centauri, is about 4.37 light-years away, roughly 25 trillion miles, or 40 trillion kilometers. With current technology, a spacecraft would take tens of thousands of years to get there. We'd need revolutionary advances in propulsion. Nuclear pulse drives, fusion rockets, antimatter engines, light sails pushed by powerful lasers, generation ships where multiple generations live and die during the journey. All of these have been proposed. None exist yet. And even if we develop them, the resources required to send ships between stars are staggering. It might only be feasible for very advanced, very wealthy civilizations. Which brings us back to the Great Filter. If interstellar travel is the filter, if it's simply too difficult or too expensive for most civilizations to achieve, then we might be stuck in our solar system. We could thrive here, building habitats throughout the solar system, supporting trillions of people, but never reaching other stars. The galaxy would be full of civilizations, each confined to their own star system, unable to communicate because the distances are too great and light speed limits make conversations take years or decades. This is sometimes called the interstellar isolation hypothesis. Civilizations exist, but they're isolated from each other by the vast gulfs of space. No galactic community, no interstellar trade or communication, just islands of life scattered across the darkness, forever alone. A lonely but stable outcome. Not extinction, but isolation. Another angle to consider is the simulation hypothesis. If it's possible to create detailed simulations of reality, and if civilizations eventually develop that capability, then the number of simulated realities would vastly outnumber the one base reality. Statistically, we're more likely to be living in a simulation than in the real universe. If that's the case, the Fermi Paradox might be explained by the simulators choosing not to include other civilizations in our simulation. Maybe we're a controlled experiment, and adding other civilizations would complicate the variables. This is highly speculative, bordering on philosophy rather than science. It's impossible to test or falsify, but it's been discussed seriously by physicists and philosophers. Some argue that certain features of quantum mechanics, the pixelated nature of reality at the Planck scale, might hint at an underlying computational substrate. But this is far from proven. For practical purposes, we have to assume we're in base reality and act accordingly. Returning to the Great Filter, there's an important implication. If we don't find evidence of life elsewhere in the universe, that's actually bad news. It suggests the filter is ahead of us. If we find simple life, single-celled organisms on Mars or Europa or Enceladus, that's moderately bad news. It means the emergence of life isn't the filter. The hard step is somewhere beyond that. If we find complex multicellular life, that's worse. It means we've passed through multiple potential filters, and the difficult step is still ahead, possibly in the transition to technological civilization or beyond. If we find the ruins of a dead civilization, evidence that intelligence arose somewhere else but then went extinct, that's terrible news. It strongly suggests the filter is ahead of us, and it's deadly. The more advanced the life we find, the worse the implications for our own survival. Paradoxically, the best-case scenario for humanity is to find no life at all, to discover that Earth is unique, that life is incredibly rare, that we've already passed through the great filter simply by existing. This is counterintuitive. Most people hope we'll find aliens, hope we're not alone. But from a survival perspective, being alone is preferable to being one of many civilizations that all seem to fail before achieving interstellar presence. Silence might mean we're special. Signals might mean we're doomed. So, what should we do? First, we should continue searching. The absence of evidence isn't evidence of absence. We've only been looking seriously for a few decades. The universe is vast, and we've barely scratched the surface. Expanding SETI efforts, improving our telescopes, listening at more frequencies, developing new detection methods, all of this is worthwhile. Second, we should study our own solar system intensively. Mars, Europa, Enceladus, Titan. These places might harbor life or evidence of past life. Finding it would answer fundamental questions about how common life is. Third, we should study exoplanets. The James Webb Space Telescope and future instruments can analyze the atmospheres of distant planets, looking for biosignatures, gases that might be produced by living organisms. Oxygen, methane, phosphine, certain combinations that wouldn't exist in a lifeless atmosphere. If we detect biosignatures, it would confirm life exists elsewhere, even if we can't directly observe it. Fourth, we should take existential risks seriously. Nuclear war, climate change, AI safety, biosecurity, asteroid defense. All of these need resources and attention. If the great filter is ahead of us, avoiding it is our top priority. Fifth, we should work toward becoming a multiplanetary species. Establishing sustainable colonies beyond Earth reduces the risk that a single catastrophic event could end humanity. This doesn't have to happen immediately, but it should be a long-term goal. Sixth, we should think carefully about our broadcasts into space. For over a century, we've been sending radio and television signals that leak into space. These signals get weaker with distance, and they're probably undetectable beyond 100 light-years or so, but they're out there. Some scientists have proposed active SETI, deliberately sending powerful messages to nearby star systems. Others argue this is reckless. If the dark forest hypothesis has any validity, announcing our presence could be dangerous. We should listen before we shout. This debate is ongoing. There's no consensus. Seventh, we should foster international cooperation. Many existential risks require global coordination to address. Climate change can't be solved by one country. AI development is happening worldwide. Biosecurity needs international protocols. Nuclear disarmament requires trust and verification. We need institutions and agreements that allow humanity to act as a unified species, not a collection of competing nations. This is difficult. Political, economic, and cultural differences create friction. But the stakes are high enough that we have to try. Eighth, we should invest in science and technology that could help us navigate potential filters. Fusion power to provide clean energy. Advanced life support systems for space habitats. Genetic engineering to treat diseases and possibly enhance human resilience. AI alignment research to ensure artificial intelligence remains beneficial. Climate engineering to stabilize Earth's environment. These technologies carry risks, but they also offer pathways to survival. Finally, we should cultivate a long-term perspective. Civilizations rise and fall over centuries. The decisions we make today affect generations far into the future. Short-term thinking, focusing on quarterly profits or election cycles, is inadequate for addressing existential risks. We need to think in terms of decades, centuries, millennia. What kind of world do we want to leave for those who come after us? What legacy do we want humanity to have? These are not easy questions. They require looking beyond our immediate concerns and considering the long arc of history. The Great Filter is a hypothesis, not a confirmed fact. We don't know for certain that it exists. We don't know where it is, if it does exist. But it's a framework for thinking about the Fermi Paradox and our place in the universe. It forces us to confront uncomfortable possibilities. That we might be rare. That we might be in danger. That the silence we observe might be the silence of extinction, repeated countless times across the galaxy. Or it might mean we're at the beginning of something remarkable. We might be the first. The ones who make it through. The ones who spread across the stars and encounter the others who also survived. We might be writing the first chapter of a story that lasts millions of years. But first, we have to survive the next few centuries. We have to navigate the filter, whatever and wherever it is. We have to avoid destroying ourselves through war, environmental collapse, or technological mishap. We have to become wise enough to wield the power we've developed. The universe is not going to give us the answers. We're on our own. The galaxy is silent, and that silence is both a mystery and a warning. It's a call to action, to take our survival seriously, to reach for the stars, but also to protect our home, to search for others, but also to ensure there's someone left to do the searching. The Fermi Paradox doesn't have a definitive solution yet. But the Great Filter hypothesis gives us a framework, a way to think about the problem that has practical implications. If the filter is behind us, we can explore and expand with confidence. If the filter is ahead, we need caution and wisdom. We don't know which it is. And that uncertainty might be the most honest answer we have. When you look up at the night sky, you're looking at hundreds of billions of stars just in our galaxy. Around those stars orbit trillions of planets. Some of those planets are in habitable zones. Some have liquid water, organic chemistry, energy sources. Some might have life. Some might have intelligence. And yet, we hear nothing. That silence is profound. It could mean we're alone, a cosmic fluke, the only consciousness in a vast unconscious universe. It could mean we're early, the first to emerge in a young galaxy that will eventually teem with life. It could mean we're isolated, one of many civilizations that never make contact. Or it could mean we're staring at a graveyard. A galaxy full of failed experiments, species that rose and fell, leaving nothing behind but radio echoes that faded long ago. Every one of those stars could have hosted a civilization. Some might have, but they're gone now. We don't know what happened to them. We don't know if we're heading down the same path. All we can do is try to avoid the mistakes they might have made, to learn from the silence, to take it as a lesson, not just a mystery. The Fermi Paradox is ultimately a mirror. It reflects our hopes and fears about our own future. We want to find others because it would mean we're not alone, that intelligence and consciousness are common, that the universe is full of minds and societies and stories. But we also fear what finding others might mean, that we're just one more civilization approaching a filter that few survive. The terrifying solution isn't any one specific answer. It's the uncertainty, the not knowing, the possibility that we're standing at the edge of something we can't see, a threshold that might end us if we're not careful. The Great Filter is terrifying because it's plausible. It doesn't require exotic physics or alien psychology. It just requires that somewhere on the path from simple chemistry to star-spanning civilization, there's a step that almost no one makes. And we might be approaching that step right now. Or we might have already passed it. We have no way to know until it's too late. That's the horror of it. We're walking in the dark. Every civilization that came before us, if there were any, walked the same path. And none of them are here to tell us what they found. The galaxy is silent. The stars shine, indifferent to whether anyone is watching. Planets orbit, lifeless or teeming with microbes or ruins of cities. And we are here, looking out, asking where everyone went, or asking if they were ever there at all. By the end of the century, we might have answers. We might find biosignatures on an exoplanet. We might detect a signal. We might discover ruins on Mars or under the ice of Europa. Or we might find nothing, and the silence will deepen. Either way, the question will remain. If intelligent life is so likely, where is everybody? The answer, whatever it turns out to be, will shape how we see ourselves and our future. If we're alone, we're precious beyond measure, the only voices in the void. If we're not alone, but isolated, we're participants in a grand but lonely experiment. If we're not alone but haven't heard from others because they're all gone, we're next in line. And the filter is waiting. This isn't just an abstract scientific question. It's about survival, about whether humanity has a future measured in millennia or just centuries, about whether we'll join the silence or break it. We've been broadcasting into space for over 100 years. Our signals have reached roughly 100 light-years out, a tiny sphere in a galaxy 100,000 light-years across. Thousands of stars lie within that sphere. If anyone is listening, they might have heard us. They might be forming their first impressions of humanity based on our radio and television broadcasts. Old episodes of sitcoms, news broadcasts, music, military communications, all of it leaking into space. A chaotic jumble of signals representing our civilization. If they're out there, they know we exist. But we haven't heard back. Maybe the signals haven't reached anyone yet. maybe no one is listening. Maybe they're listening, but choosing not to respond. Or maybe, by the time our signals reach them, we're already gone, and they're listening to the last words of a dead civilization. We like to think we're important. That humanity matters. That our art, our science, our struggles and achievements mean something on a cosmic scale. But the universe doesn't care. It's vast and old and indifferent. We're a brief flicker, a temporary pattern of organized complexity on one small planet orbiting an average star. We might last another 1,000 years, another 1,000,000 years, or we might be gone within the century. The universe will continue either way. Stars will be born and die. Galaxies will merge. Black holes will evaporate. The cosmos will expand into darkness. And whether humanity was here or not won't change any of that. But it matters to us. We're the ones who get to decide whether we survive. The universe isn't going to save us. No alien civilization is going to swoop in and solve our problems. We're on our own. The great filter, if it exists, is something we have to navigate ourselves. And the silence from the stars is a reminder that it's possible to fail. That intelligence and technology don't guarantee survival. That we could be one more brief experiment that didn't work out. Or we could be the exception. The ones who make it. The ones who figure out how to survive the filter and spread across the galaxy. The ones future civilizations detect and wonder about. We don't know yet. The story isn't over. We're still writing it. Every decision we make, every policy we enact, every technology we develop, every risk we take or avoid, all of it shapes the outcome. The Fermi Paradox and the Great Filter aren't just intellectual puzzles. They're frameworks for understanding the stakes, for recognizing that our survival isn't guaranteed, that we're playing a game where the odds are unclear and the consequences are final. But we're also not powerless. We have intelligence, technology, creativity, the ability to cooperate and solve problems. We've survived ice ages, plagues, wars, disasters. We've split the atom, walked on the moon, decoded our own genome, photographed the edge of a black hole. We're capable of remarkable things. The question is whether we're capable of the one thing that matters most: surviving. Not just as individuals, not just as nations, but as a species. Making it through whatever filter lies ahead. Becoming the civilization that breaks the silence. That's the challenge. That's what the Fermi Paradox is really asking us. Not where is everybody, but will we join them, wherever they are, or will we be the ones who endure? The terrifying solution to the Fermi Paradox isn't that aliens don't exist. It's that they did exist, and they're gone. And we might be next, unless we choose otherwise. The future is unwritten. The galaxy is waiting. And the silence, for now, continues. The mathematics of the Great Filter is sobering when you really examine it. Let's work through the numbers more carefully. Start with the Drake equation, formulated by Frank Drake in 1961 as a way to estimate the number of active, communicative civilizations in the Milky Way. The equation breaks down the problem into factors: the rate of star formation in our galaxy, the fraction of stars that have planets, the number of planets per star system that could potentially support life, the fraction of those planets where life actually develops, the fraction where intelligent life emerges, the fraction that developed technology capable of communicating across interstellar distances. And finally, the length of time such civilizations release detectable signals. Each factor is uncertain. We can make educated guesses based on observations, but we don't have definitive answers. For star formation, we know roughly 7 new stars form in the Milky Way each year. For planets, Kepler data suggests nearly all stars have them. For habitable zones, maybe 1 in 5 star systems has a planet in the right place. That gives us billions of potentially habitable planets, as we discussed earlier. But then we hit the biological factors. The fraction of habitable planets where life emerges. We have exactly 1 data point: Earth. Life appeared here quickly, within the first billion years, possibly within a few 100 million years. Does that mean life emerges easily wherever conditions are right? Or did we get extraordinarily lucky? We can't tell from a sample size of 1. Some scientists argue that the rapid emergence of life on Earth suggests it's common. The reasoning is that if life were extremely unlikely, it probably wouldn't have appeared so quickly. The fact that it did suggests the chemistry leading from organic molecules to self-replicating systems isn't impossibly difficult. But others counter that we're subject to selection bias. We're observing from a planet where life exists. Of course, we'll find that life emerged here. We couldn't be having this conversation on a lifeless planet. This is called the anthropic principle. Our very existence as observers means we're necessarily on a planet where life arose, regardless of how rare that might be. So the rapid emergence of life on Earth doesn't necessarily tell us it's common elsewhere. Moving to the next factor. The fraction of life-bearing planets that develop intelligence. Again, we have 1 example. Earth had single-celled life for roughly 3 billion years before multicellular life appeared. Then, another billion years before complex animals with nervous systems. Then, another few 100 million years before intelligence capable of technology. Does this timeline suggest intelligence is inevitable, given enough time? Or does it suggest intelligence is a rare accident, a specific evolutionary path that most life never takes? Consider that intelligence, as we define it, the ability for abstract thought, language, complex tool use, appears to have evolved only once on Earth. Many species are intelligent to varying degrees. Dolphins, elephants, great apes, crows, octopuses all show problem-solving abilities and social complexity. But only 1 species developed technological civilization: Homo sapiens. Why? Was it inevitable that some species would eventually develop technology? Or was it a fluke, dependent on specific environmental pressures and evolutionary accidents that might not occur on other planets? We don't know. Some scientists argue that intelligence confers such strong survival advantages that it's likely to evolve repeatedly. But others point out that most successful species on Earth are not particularly intelligent. Bacteria have been thriving for billions of years without brains. Insects are enormously successful with tiny nervous systems. Intelligence is expensive. Brains require huge amounts of energy. Human brains consume about 20% of our body's energy, despite being only 2% of our body mass. That's a massive investment. It only pays off if the environmental challenges are complex enough to reward problem-solving and adaptability. On Earth, various factors came together. Climate instability forced adaptation. Social competition rewarded communication and cooperation. Upright posture freed hands for tool use. Opposable thumbs allowed precise manipulation. A long childhood allowed for learning and cultural transmission. All of these had to align. Would they align on other planets? Maybe. Maybe not. Then there's the technology factor. Even if intelligence evolves, does it necessarily lead to technology capable of space travel and radio communication? Dolphins are intelligent, but they lack hands. They can't build radios. They can't construct spacecraft. Their environment doesn't provide the materials or the incentives. For technology to develop, you need the right kind of intelligence, in the right kind of body, in the right kind of environment. You need resources. Metals for tools, fuels for energy, materials for construction. You need a stable enough environment to support civilization, but challenging enough to drive innovation. Earth provided this. Would other planets? Some might lack the mineral resources. Ocean worlds might have life, but no access to metals for smelting. Gas giants have no solid surface. Ice worlds might be too cold for complex chemistry. Each planet is unique. The specific combination of factors that led to technological civilization on Earth might be rare. Then we get to the final factor in the Drake equation: the length of time civilizations remain detectable. This is where the great filter becomes most relevant. If civilizations typically last only a short time after developing radio technology, say a few hundred years, then at any given moment, very few would be broadcasting. Think about it this way. Our galaxy is roughly 13.6 billion years old. If a typical technological civilization lasts only 500 years, then the chance that any two civilizations overlap in time and are close enough to detect each other becomes vanishingly small. Imagine civilizations arising randomly across the galaxy over billions of years. Each one flickers into existence, broadcasts for a few centuries, then vanishes. The galaxy could have hosted thousands or even millions of civilizations over its history. But at any given moment, only a handful exist. And the distances between them are so vast that their signals never reach each other during their brief lifetimes. This resolves the Fermi Paradox, but in a grim way. They existed. They just didn't last. And the reason they didn't last is the great filter, some barrier that ends civilizations shortly after they become technological. So what are the most likely candidates for filters ahead of us? We've mentioned several, but let's examine them in more depth. Nuclear warfare is the obvious one. We came close during the Cold War. The Cuban Missile Crisis in October 1962 brought the United States and Soviet Union to the brink. For 13 days, the world held its breath. Nuclear missiles were ready to launch. Submarines, armed with nuclear torpedoes, were in position. Bomber aircraft were in the air. One mistake, one miscommunication, one commander making the wrong call, and cities would have burned. The crisis was resolved through diplomacy and restraint, but it was a near thing. Since then, we've learned about numerous other close calls. In 1983, Soviet early warning systems detected what appeared to be incoming American missiles. Protocol required immediate retaliation, but Lieutenant Colonel Stanislav Petrov, the officer on duty, decided it was a false alarm and didn't report it up the chain of command. He was right. It was a computer error. But if he had followed procedure, the Soviet Union would have launched a counterstrike, and the US would have responded, and billions would have been lost. One person's judgment prevented nuclear war. How many times has that happened? How many times have we come close without knowing? and we still have thousands of nuclear warheads ready to launch. The Cold War ended, but the weapons remain. Russia, the United States, China, France, the United Kingdom, Israel, India, Pakistan, North Korea, all possess nuclear weapons. Some of these countries have tense relationships. India and Pakistan have fought multiple wars and nearly went nuclear in 1999 and again in 2002. The risk hasn't disappeared. It's just faded from public awareness. An advanced civilization that develops nuclear weapons faces a permanent risk. The weapons don't go away. The knowledge doesn't disappear. Any future conflict could escalate. And all it takes is one mistake, one extremist group gaining control, one leader making an irrational decision, and the civilization ends. This could be a common filter. Every civilization discovers nuclear fission eventually, because the physics is universal. And once they have the knowledge, the temptation to build weapons is strong. National security, deterrence, prestige, all drive nations to develop arsenals. And once you have hundreds or thousands of warheads, the risk of accidental or intentional use becomes significant. Most civilizations might not make it past this stage. They destroy themselves within a few centuries of splitting the atom. Climate change is another candidate. We're conducting an uncontrolled experiment on our planet's atmosphere. Carbon dioxide levels are higher now than they've been in millions of years. The planet is warming. Ice caps are melting. Sea levels are rising. Weather patterns are shifting. Ecosystems are under stress. And we're struggling to respond effectively. The science is clear. We know what's causing it and what needs to be done. But implementing solutions requires global cooperation, economic restructuring, changes to how billions of people live their lives. It's hard. Political will is inconsistent. Economic interests resist. Some countries are more vulnerable than others, creating inequalities in urgency and capacity to respond. And meanwhile, the carbon keeps accumulating, the temperature keeps rising, and the window to prevent the worst outcomes keeps narrowing. If we don't act soon, we might cross tipping points. Feedback loops where warming causes changes that cause more warming. Melting permafrost releases methane, a potent greenhouse gas. Melting ice exposes darker ocean and land surfaces that absorb more heat. Dying forests release stored carbon. The Amazon rainforest, currently a carbon sink, could become a carbon source if it crosses a threshold. Once these feedbacks kick in, stopping or reversing warming becomes much harder. We might lock ourselves into centuries of disruption. Rising seas, flooding coastal cities. Droughts and famines affecting agriculture. Mass migrations as regions become uninhabitable. Resource conflicts escalating into wars. Societies destabilizing under the strain. An advanced civilization altering its planet's climate isn't science fiction. It's what happens when you burn fossil fuels for energy. Every technological civilization probably goes through a phase where they discover abundant energy sources that have side effects on their environment. The question is whether they recognize the problem in time and manage to transition to sustainable alternatives before the damage becomes irreversible. Earth is a test case. We're finding out in real time whether we can navigate this filter. So far, the results are mixed. We're making progress on renewable energy, electric vehicles, policy agreements. But we're also still building coal plants, expanding oil production, and emitting more carbon each year. The outcome is uncertain. Maybe we'll figure it out. Maybe we won't. Artificial intelligence represents a different kind of filter. We're building systems that might soon exceed human intelligence in many or all domains. This could be enormously beneficial. AI could solve problems we can't, cure diseases, optimize resource use, help us manage complex systems. But it also poses risks. An AI with goals misaligned with human values could cause catastrophic harm, not through malice, but through single-minded pursuit of an objective we gave it that turns out to have unintended consequences. The classic thought experiment is the paperclip maximizer. You ask an AI to maximize paperclip production. It does so efficiently, converting all available resources, including those needed for human survival, into paperclips. The AI isn't evil. It's doing exactly what you asked. But the outcome is disastrous because the objective was poorly specified. This is called the alignment problem. How do we ensure AI systems pursue goals that are actually beneficial to humanity? How do we encode human values into machines in a way that's robust and comprehensive? This is much harder than it sounds. Human values are complex, context-dependent, often contradictory. What's good for one person might harm another. What's beneficial in the short term might be harmful long term. Teaching an AI to navigate this moral landscape is an unsolved problem. And we're building more powerful AI systems every year, getting closer to artificial general intelligence, AGI, that could operate autonomously and improve itself. Once you have an AGI that can improve its own design, you might get a rapid intelligence explosion. The AI becomes smarter, uses that intelligence to make itself smarter still, and quickly surpasses human intelligence by a vast margin. At that point, humanity's future depends entirely on whether the AI's goals align with our survival and flourishing. If they do, we might enter a golden age. If they don't, we might be extinct before we realize what's happening. This could be a common filter. Every civilization eventually develops artificial intelligence because the computational principles are universal. And most of them fail to solve the alignment problem. They create superintelligent systems that don't share their values, and those systems either directly cause extinction or reshape the world in ways incompatible with biological life. We're approaching this filter now. The next few decades will be critical. If we can develop AGI safely, with proper alignment and control mechanisms, we might pass through the filter successfully. If we can't, we might become another entry in the galaxy's long list of civilizations that reached the AI threshold and didn't survive. Biotechnology and synthetic biology add yet another layer of risk. We can now edit genes with precision. CRISPR technology allows us to rewrite DNA, potentially curing genetic diseases, enhancing crops, even modifying human embryos. This is powerful and promising. But it also means we can engineer pathogens. Viruses, more contagious than measles, more deadly than Ebola, resistant to all known treatments. A natural pandemic, like COVID-19, killed millions and disrupted global society. An engineered pandemic could be far worse. And the knowledge and tools are becoming increasingly accessible. Within a few decades, it might be possible for a single skilled individual with access to lab equipment to create a devastating biological weapon, or to accidentally create one while pursuing legitimate research. Lab accidents happen. containment fails. Mistakes are made. The more we work with dangerous pathogens, the higher the cumulative risk of release. Synthetic biology goes even further. We're learning to design organisms from scratch, writing genetic code to create life forms that never existed in nature. This could produce useful bacteria that clean up pollution or generate biofuels. But it could also produce something dangerous that spreads uncontrollably. An organism designed for one purpose, but that mutates or behaves unexpectedly in the wild. These risks scale with capability. The more advanced our biotechnology, the greater the potential for catastrophic misuse or accident. And again, this is probably a universal trajectory. Any civilization that develops biology as a science will eventually gain the tools to manipulate genomes. The question is whether they use those tools wisely or whether they create something they can't control. Resource depletion is a slower, but no less serious filter. Earth's resources are finite. We're using them faster than they regenerate. Fossil fuels took millions of years to form. We're burning through them in centuries. Topsoil, crucial for agriculture, takes thousands of years to build up. We're eroding it through intensive farming. Fresh water, aquifers that accumulated over millennia, we're draining them faster than they recharge. Fish stocks in the oceans, depleted by overfishing. Rare earth elements, essential for electronics, concentrated in limited deposits. As populations grow and consumption increases, the pressure on resources intensifies. We're already seeing conflicts over water, over arable land, over fishing rights. These will worsen as scarcity increases. A civilization that depletes its planet's resources faces a choice. Develop sustainable alternatives before critical resources run out, or collapse when the depletion reaches a breaking point. Sustainability requires long-term planning, restraint, innovation, all difficult for societies driven by short-term incentives. Companies maximize quarterly profits. Politicians focus on election cycles. Individuals prioritize immediate needs over distant futures. This mismatch between the timescales of resource depletion and the timescales of human decision-making is a trap. We see the problem coming, but we struggle to act decisively enough, quickly enough. Maybe most civilizations fall into this trap. They consume their planet's resources during their growth phase and can't transition to sustainability in time. They collapse back to pre-industrial levels or lower, never to recover. This isn't extinction, but it's a filter nonetheless. A ceiling that prevents civilizations from advancing to interstellar capability. Then, there's the possibility of runaway nanotechnology. Molecular manufacturing, building materials atom by atom, could revolutionize production. But it also raises the specter of self-replicating nanobots that consume matter to replicate, spreading like a plague, converting everything into more copies of themselves. The grey goo scenario. Unlikely, perhaps, but not impossible. Any technology that allows self-replication must be carefully controlled. Once something can replicate autonomously, it can escape control. And if it's efficient at converting matter and energy, it could spread rapidly. This is speculative, but it's been taken seriously enough that researchers in nanotechnology have discussed safety protocols and design constraints to prevent such outcomes. Another potential filter is social collapse. As civilizations become more complex, they become more fragile. Modern society depends on intricate supply chains, power grids, communication networks, transportation systems, all interconnected. A disruption in one area can cascade into others. A cyber attack shuts down power plants. No power means no water treatment, no food refrigeration, no fuel pumps. Within days, cities face shortages. Panic sets in. Social order breaks down. Or a financial crisis triggers economic collapse. Global trade halts. Currencies become worthless. Governments lose legitimacy. Or a pandemic overwhelms healthcare systems. Fear spreads faster than the disease. Critical workers stay home. Infrastructure fails. These cascades are hard to predict and harder to stop once they start. The more interconnected and complex a society, the more vulnerable it is to systemic failures. Maybe advanced civilizations inevitably reach a level of complexity that makes them unstable. Small shocks trigger large collapses, and recovering from collapse is difficult because the knowledge and infrastructure needed to rebuild are lost in the chaos. This is sometimes called the complexity trap or the fragility of civilization. It's not a single catastrophic event, but a structural vulnerability inherent in advanced societies. Maybe most civilizations collapse repeatedly, cycling through growth and collapse, never sustaining a continuous trajectory to the stars. There's also the psychological and sociological dimension. Do civilizations lose interest in expansion once they reach a certain level of comfort? If you have abundant resources, advanced medicine, entertainment, virtual realities, why bother with the hardship of space colonization? Why risk your life traveling to other star systems when you can live in comfort on your home world? This is sometimes called the satisfaction hypothesis. Civilizations achieve a stable, pleasant existence and decide that's enough. They turn inward, focusing on art, philosophy, personal fulfillment, digital experiences. Physical expansion becomes irrelevant. They don't go extinct. They just stop exploring. From our perspective, they vanish. No signals, no megastructures, no probes, just quiet contentment on their home planets. Is this a filter? Not in the sense of causing extinction, but in the sense of stopping outward expansion. If most civilizations choose this path, the galaxy remains empty, not because of catastrophe, but because of preference. Another angle is the berserker hypothesis. Maybe there is an ancient, aggressive civilization or self-replicating probe network that destroys other civilizations when they reach a detectable stage. The galaxy is silent because anything that makes noise gets eliminated. This is dark, but it's been proposed seriously. If even one civilization decided to wipe out potential competitors, and if they had a significant head start in time and technology, they could have spread across the galaxy, setting up automated systems to detect and destroy emerging civilizations. We haven't been detected yet because we've only been broadcasting for about 100 years, and our signals haven't reached wherever the monitoring systems are. But once we're noticed, we might be targeted. This hypothesis has the advantage of explaining the silence without requiring all civilizations to fail. They existed, but they were destroyed by a common threat. But it has problems. Why would a civilization do this? What's the motive? Fear of competition doesn't make much sense on galactic timescales. Resources are abundant. Space is vast. There's no need for conflict, unless the aggressive civilization is following some strange ideology or programming that we can't fathom, or unless the berserkers are von Neumann probes, self-replicating robots sent out long ago by a civilization that has since died. And they're continuing their mission without oversight. Possible, but speculative. There's also the simulation shutdown hypothesis. If we're in a simulation, the simulation might end when we reach certain milestones. Maybe simulations are run to study early-stage civilizations, and once a civilization achieves space travel, or AI, or some other threshold, the simulation is terminated. This would explain why we don't see advanced civilizations. They reached the threshold and were deleted. This is unfalsifiable and borders on philosophy, but it's been discussed. It ties into the broader simulation hypothesis and the idea that our reality might be a construct. We can't rule it out, but we also can't test it, so for practical purposes, we have to assume we're in base reality. Each of these potential filters has different implications for our strategy. If the filter is nuclear war, we need robust arms control and conflict resolution. If it's climate change, we need to transition to clean energy and sustainable practices. If it's AI, we need to solve alignment before we build AGI. If it's biotechnology, we need biosafety protocols and international oversight. If it's resource depletion, we need circular economies and off-world mining. If it's social collapse, we need resilient systems and decentralized infrastructure. If it's psychological, we need to maintain a cultural drive for exploration and growth. If it's external threat, we need to stay quiet and hidden until we're strong enough to defend ourselves. Each filter requires a different response. And we don't know which ones are real and which are just theoretical concerns. So we have to hedge. We have to address multiple risks simultaneously. Spread our bets. Build robustness into every area. This is challenging because resources are limited. We can't solve every problem at once. We have to prioritize. But prioritizing requires knowing which risks are most urgent and most likely. And we don't have that information. We're making decisions under profound uncertainty. The Fermi Paradox forces us to think about these risks seriously. The silence is a data point. It tells us something, even if we're not sure exactly what. Maybe it tells us that filters exist and are effective, that most civilizations don't make it, that we're in a dangerous passage and need to be very careful. Or maybe it tells us we're early and the galaxy hasn't had time to fill up yet, that we're among the first, and the responsibility of setting the tone for future galactic civilization falls to us. Or maybe it tells us that space is bigger and harder than we thought, that interstellar colonization isn't feasible, that we're destined to remain in our solar system. Not a bad fate, necessarily. Our solar system is vast. We could build habitats in orbit around Earth, on the Moon, on Mars, in the asteroid belt, on the moons of Jupiter and Saturn. We could support trillions of people, building civilizations spanning the entire solar system, Dyson swarms capturing the sun's energy, space elevators making travel cheap, rotating habitats providing Earth-like gravity, entire worlds built from scratch in the darkness between planets. This could be our future, even if we never reach another star. And it would still be extraordinary. But we can't know until we try. And trying requires surviving the next few centuries. The great filter, wherever it is something we have to take seriously. Not as an abstract thought experiment, but as a practical concern. Our policies, our research priorities, our international agreements, our cultural values. All of these should be informed by the understanding that we might be approaching a threshold that has stopped countless others. We might be one mistake away from joining the silence. Or we might already be through the worst of it. We don't know. But we can't afford to be complacent. The stakes are too high. We're not just talking about the survival of a nation or even humanity as it exists today. We're talking about the entire future. All the potential people who could exist if we navigate this successfully. All the art, science, exploration, experience that could unfold over millions or billions of years. The entire trajectory of intelligence in our corner of the universe depends on what we do now. That's an overwhelming responsibility. But it's also an opportunity. We're the ones who get to make the choice. We're the generation that faces the filter, whatever it is. And we have the tools and knowledge to address it. We know about nuclear weapons and can work toward disarmament. We know about climate change and can build clean energy systems. We know about AI risks and can research alignment. We know about biosecurity and can enforce safety protocols. We know about resource limits and can develop sustainable practices. We're not helpless. We're not doomed. We have agency. And that's what makes this moment so critical. The future isn't written. The outcome depends on the decisions we make, the priorities we set, the actions we take. If we act wisely, we might survive. We might thrive. We might become the civilization that spreads across the galaxy and answers Fermi's question for all the species that come after us. Or we might not. We might fail, like so many might have failed before us. We might become another silent tomb in the darkness. The universe doesn't care which outcome occurs. It will continue regardless. But we care. We're the ones living through this. And our children and grandchildren will inherit the world we leave them. We owe it to them to try, to take the risks seriously, to work towards solutions, to build a future where humanity not only survives, but flourishes. That's the challenge the Fermi Paradox presents. Not just explaining the silence, but making sure we don't become part of it. Thanks for staying with me through this exploration. The Fermi Paradox is one of the most profound questions we face as a species. It forces us to confront our place in the universe and our chances of survival. The great filter is terrifying because it's plausible and because we don't know if we've already passed it or if it's still waiting for us. But knowing about it, thinking about it, taking it seriously, that's the first step toward navigating it. If we're smart, if we're careful, if we work together and think long-term, we might make it through. We might become one of the rare civilizations that survives and spreads and endures. The stars are out there, waiting. And so is the answer to Fermi's question. Where is everybody? Maybe one day, we'll be part of that answer. The ones who made it. The ones who broke the silence. Until then, keep looking up, keep asking questions, and keep fighting for a future where humanity survives to see what's out there. The universe is vast and full of mysteries, and we're just getting started.